This unit is exponential and logarithmic functions. It's out of chapter 9 in our textbook. We're going to be working with sections 9.3 to 9.2 to 9.8 in that textbook. I've uploaded the pages of the textbook to Schoology in case folks don't have their textbooks with them in remote learning. So just make sure that you look at those documents and you can download that chapter to your computer and reference it for homework. Okay, so first we're going to talk about perfect squares and perfect cubes. So there was a unit that we weren't able to do just yet in remote learning, so this is kind of a fast way to go through some key components of perfect squares and perfect cubes. So here I have 2 squared, I have 4, 3 squared, 9, and 4 squared is 16. So all of these numbers, 4, 9, and 16, are perfect squares. So that means when we take the square roots of them, we could say the square root of 4 is 2, the square root of 9 is 3, and the square root of 16 is 4. Okay, so that's something we're all familiar with. But now when we're talking about perfect cubes, we have 2 to the 3rd power, and that gives us 8. And then think about what 3 to the 3rd power is. Don't say 9, a lot of people make that mistake, but it's 3 times 3 times 3, which is 27. 4 to the 3rd, we have 64. And 5 times 5 times 5, we have 125. So in order to undo something that's being cubed, we can take the cubed root. Okay, we could take the cubed root. So these are cubed roots. And we could say, all right, well, the cubed root of 8. So what multiplied by itself 3 times gives us 8? And that's 2. The cubed root of 27. What multiplied by itself 3 times gets us 27? 3. And we could do this for the next 2. Okay? So here we have square roots. And we have cubed roots on the right. Okay? So for a radical, right, we've taken square roots. When there is no number in this area region here, we have to assume it's a square root. Okay, but if there's a 3 there, that means this is a cubed root. And that's the index of the root. And then something underneath the radical is the radicand. So this is all information from geometry last year, except now we have this cubed root that we're thinking about. Okay, so now we're going to talk about exponents. All right, we have, what does an exponent of 1/2 and 1/3 do? So 4 to the 1/2 is the same thing as saying take the square root of 4. 4 is a base. 1/2 is the exponent. So if the exponent is 1/2, that's equivalent to a square root. So let's look at the one below it. We have 12 to the 1/2. So that is the square root of 12. And then we can simplify the square root of 12. I know factors of 12 are 4 and 3, so I have 2√3 that this simplifies into. And kind of going back to that one, we have 2, right? The square root of 4 is 2. So if on the left we see the 4 to the 1/2 and 12 to the 1/2 are square roots, what do you suppose 8 to the 1/3 is? 8 to the 1/3 is a cubed root, and the cubed root of 8 is 2. Okay, 8 is a perfect cube. So for this one, we have the cubed root of 24, and we have to think now of factors of 24, and one of the factors of 24 is a perfect cube. So thinking about these numbers, these are all perfect cubes. 2 times 2 times 2 is 8, 3 times 3 times 3 is 27, 4 times 4 times 4 is 64. So these are the numbers that we're looking for. And when we're taking square roots, we want to look for perfect squares, which is why with the square root of 12, we had 4 and 3. We wanted a 4 because we could take the square root of 4 and get 2. So factors of 24 that are perfect cubes, I have 8, right? The cubed root of 8 is 2. And then let's think. The cubed root of 3 has to just stay as the cubed root of 3. Right? So if you think about what a cubed root is, it's a number multiplied by itself 3 times. We need to get that underneath the radical. Okay, so exponent, a base raised to a half is a square root, and a base raised to 1/3 is a cubed root. Okay, so now for these, we want to simplify using properties of exponents. And if we think about this, we know that if we have a power, right, an exponent raised to an exponent, we have our base is 4, we have to multiply these. So this is equivalent to 4, and then 1/2 times 3, that gives us 3/2. Okay, so when we're looking at that, 4 to the 3/2, this looks a little tricky, but what if we looked at what's inside of the parentheses first? Okay, 4 to the 1/2 we know is the square root of 4. And now we're raising that to the 3rd power. Okay, and then the square root of 4 is 2. And then still raising that to the 3rd power, so we have 8. Okay, so when we're looking at this, notice how when we take the square root, okay, and then we raise it to another exponent, we end up with 4 to the 3/2. So 4 to the 3/2 is equivalent to the square root of 4 to the 3rd. Okay. So the way that I like to remember this, the power is always in the numerator, and then the index is always in the denominator of that fractional exponent. Okay. So if we're looking at this next example, we have 2 is in the numerator, so that's the whole power after we take the cubed root of 8. Okay, so the cubed root of 8 is 2, and then we have 2 squared, which is 4. Okay, so here's the rule that we can think about. If we have a to the m over n, that can simplify to the nth root of a to m. So it's always power over root or index. Okay. So it's something that will be useful as we go through this next unit. Okay, so let's look at these 3 examples. We want to find the value of x, and where is x located in all of these equations? It's located in the exponent, okay? So if we're looking at this first one, 2 to the x equals 16. Everyone here probably is like, oh, well, I know 2 to the 4th gets us 16. 2 times 2 times 2 times 2, 16, okay? So 4 is our answer. But there's another way that we can figure this out. 16, okay, so let's look at the exponent here. We have x, and then our base is 2. So we have 2 to the x. How can we rewrite 16 that has a base of 2? So 16 can be rewritten as 2 to the 4th power. And once we notice that we have the same base, what can we do with those exponents? We can set them equal to each other, and we can solve. So if we look at the second example, we have 4 to the x plus 3 equals 4 to the 10th. So since we have the same base, we can set an equation equal to each, or we could set both those exponents equal to each other and get x equals 7. So when we have the same base on both sides of equation, set exponents equal to solve. Okay. All right, so now for this third one, we have 9 to some power gets us 27. 9 times 3 gets us 27, but 9 to some power gets me 27, so this is a bit more tricky. So let's think. We have 9. Can 9 be rewritten as a smaller base? And can 27 be rewritten with a smaller base? So 27 I know is 3 to the third. And 9 I know is 3 squared, but it's all 3 squared to the x power. So we're trying to rewrite these each side of the equation to have the same base. So here, if we have a power raised to a power, this is really 3 to the 2x equals 3 to the third. And since we have 3's set equal, we could say, all right, well, 2x equals 3, those exponents, and divide by 2, so x is 3 halves. Okay? So what that's saying is 9 to the 3 halves, does that give us 27? So remember, this is the power, that's the root, so we have the square root of 9 to the third power, so we get 3 to the third, that gives us 27. Okay? So you may have to break down these numbers into smaller bases. So this is called the one-to-one property of exponents. So take a minute to write it down. In an equation, if the bases match, then you can set the exponents equal to solve. So if b to the x equals b to the y, then x equals y. And if the bases are different, then you must break down the bases into smaller numbers so the bases match in order to use this property. Okay, so let's practice with this. We have 8 and 16, so 8. Can 8 be rewritten with a smaller base? So I have 2 to the third, gives me 8. And then I also have 2 to the fourth, gives me 16. So if I have 2 to the 3x equals 2 to the fourth, well, we have the same base. We can use that one-to-one property, set the exponents equal, and x is 4/3. Okay. So try this next one, see how you do. 125 and 25. I always just think 5. So like there should be certain numbers that you think of like bases right away. So 125 I know is 5 to the third, all to the x. And then 25 is 5 squared, all to the x minus 2. So we got 5 to the 3x equals, here's where some distributive property is going to come in, 5 to the 2x minus 4. So those exponent properties, we have to multiply those exponents. So now that we have the same base, we can use the one-to-one property of exponents and solve and get x equals -4. So we're going to finish the video by talking about what an exponential function is. This is where we're going in this unit. But exponential functions are in the form of f of x equals b to the x, where b, the base, is greater than 0. So that some things that grow exponentially, pandemics. So what we're experiencing right now, and if you're looking at the graphs of the number of cases of coronavirus and COVID-19 actually, notice how it's increasing at a rapid pace, and we've been trying to flatten the curve. Okay, we don't want it to keep going up. So this is an example of exponential growth. Bank accounts that compound, we're going to be talking about that next week. Microorganisms in cultures, right? If you see bacteria increasing at a rapid pace, that's potentially exponential growth. Human population. And then some things that decay exponentially, radioactive decay. So we're going to talk about taking half-lives of radioactive materials. So it kind of goes into, we're going to discuss the Chernobyl incident in the Ukraine, making when was it safe to go back into that area after the nuclear meltdown? Population decline, and then also cooling of water and liquid. So if you take a really cold water out of the refrigerator, freezer, and you let it sit on the counter, the rate at which it will heat up will be an exponential model. So exponential models, right? We have exponential growth and exponential decay, and that's what we're going to be discussing this whole unit as we finish out the year.